Okay, so where we left off, I teased you at the end of the first class, I know it was very exciting, with ways that you can structure models of cell growth. And we talked about how you could have structured or unstructured how you could have segregated or unsegregated descriptions of cell growth. So if you recall, in unstructured models, the cell is basically a big black box. So you've got something going in and something going out, and you have no idea what's going on in between. And in unsegregated models, again, you're looking at the average of the population as a whole, as opposed to the individual cells. So it's like the difference between looking at an ELISA and looking at flow cytometry. So how many people don't know what I'm talking about when I say that? I can describe it. Okay, so has anyone heard either of those terms? Just a couple of you. Okay, so an ELISA stands for enzyme-linked immunosorbent assay. I'm not going to test you on this. It's just important that you know as bio students. And it's a very powerful technique that allows you, it actually takes advantage of the ability of proteins to adsorb to polymers, and you use these clear plastic multi-well plates, and there are a variety of ways that you can do it. The simplest is that you stick in your protein of interest, your mixture of proteins that you're interested in, and you want to find out how much of protein A you have. Well, protein A will bind in amounts that are more or less proportional to the amount that's in the liquid. So you rinse it off, you add antibodies that are specific to protein A. Okay. And usually those, you could do it so that the antibodies directly have a marker on them that either fluoresces or has an enzyme. The traditional is enzyme linked. So like horseradish peroxidase, for example, will catalyze a colorimetric reaction. Often you have a secondary antibody that's specific to the primary one. You do that for a couple of reasons. One is that it's quite expensive to conjugate the enzyme to the antibody. So if you're looking at a bunch of really specific and expensive antibodies and then you're losing a bunch of it by conjugating your marker to it, that adds to the expense a lot. Whereas if you've got these much more generic secondary antibodies that just recognize, say, any rabbit IgG antibody, they're easy to make in quantity and they're cheaper. And then you put the marker on. And the bonus of it being enzyme linked is that you basically are amplifying, and especially the secondary binding and the enzyme linking amplifies the signal, so you can have quite a small amount of protein that you can still detect using an ELISA, specifically detect using an ELISA. But of course, what that does is it gives you an average amount. So if you were lysing cells and seeing how much on average of a certain protein your cells had, it doesn't tell you anything about the population. Okay. In contrast, a technique called flow cytometry uses a very thin capillary. So you have a solution of hundreds of thousands or millions of cells, all different, and they get sucked up through this capillary, and you can label the cells with a fluorescent antibody, or actually several differently colored fluorescent antibodies. And it shines a laser through it, and it measures how much different markers are on each individual cell. So if you have 1 million cells, you can find out that 10% of them express that marker at the same time as that marker and are probably macrophages, and another 20% of them express this marker at the same time as this other marker and are probably neutrophils, and so on. So you can really tease out individual cell dynamics with flow cytometers that you can't get with an ELISA. So both of those, especially if you do any mammalian cell biology, are really important techniques to at least understand how they work. But this is more what you would call it allows you to understand things at the segmented level. So what happens from individual cell to individual cell, and something like an ELISA just allows you to understand what's happening to the population as a whole. So you can imagine you can actually get a lot more information from something that's segmented like a flow cytometer than you can by averaging out overall what's happening. Right, any questions? Okay, so there's benefits and problems to both of those. So computational time is getting cheaper and cheaper. So theoretically, you should be able to use Monte Carlo techniques, analyze what happens to every single cell in a population, and see what the outcome would be. Similarly, if you know something about how the cells behave, you can use a structured model instead of this black box approach, and try and model what's happening biochemically within each cell. So maybe you can actually look at each cell and what's happening to each individual cell with time as they get a specific stimulus, for example. So that's obviously not easy to do, and it's not an easy modeling system. So there are problems as far as just ease go, but there are that can be solved by using a much, much simpler approach, which is the unstructured, unsegmented model. So imagining that all the cells are behaving the same way, and they're basically just black box systems. Something comes in, reliably something else comes out. And we use those a lot. But what's the problem with doing a technique like that? Super simple, really nice, easy math, looks familiar. What would be a problem with that approach? Cece?
Could miss something, like if it's super simple, it might not miss, or it might not include a nuance that you'd only think of if you knew about everything.
So that's absolutely true. And there are some particular times that those nuances are quite important. Any thoughts on when that might be in a process? So for example, when is the biochemistry of a cell changing over time? As opposed to more or less behaving repeatedly.
When it's growing, like when it's exponential growth of the population?
So if it's always within the exponential growth phase, it's actually pretty repeatable. So something relatively early in the exponential growth phase is still dividing rapidly along with something later in the exponential growth phase.
So I guess it's a transition then?
Right, so any transitions aren't covered well by these very simple, unstructured, unsegmented models. So when you're looking at lag phases, when you're looking at transitions into stationary phase and death phase, the general models do not cover what's going on well at all. Similarly, so that's in a batch process, similarly, if you've got any disruptions in the process, so things are not behaving in a constant way, you've got some sort of, like maybe you accidentally added 100 extra grams of glucose into your bioreactor, your unstructured, unsegmented model is not going to know how to deal with that effectively, because that's a big transition, like a big step change that isn't well handled by these models. So If you're trying to really, say, model a bioreactor so that you can do some of the more sophisticated process control on it that allows you to understand what happens if there are sudden perturbations to what's going on, the simple models may not effectively cover what's going on. So if you suddenly, for example, say your bioreactor is actually the way that you're treating waste from a waste treatment plant. In that case, although you might have a relatively stable population, the waste coming in and out of the bioreactor is going to fluctuate a lot. You're going to see different substrate amounts coming in, different inhibitors coming in, different nutrients available, and all of those transient disruptions won't necessarily be effectively described by the simple models that the unstructured, unsegmented approach gives you.
So is this all?
CC first and then Carl.
I was just gonna say, is there, so you can just basically sum this up as saying you can use unstructured and unsegmented approaches for steady state situations then, and then anything else you probably should use a more detailed approach?
So you can use them for steady state, and you can use them for exponential growth phase. And as long as you're not having to deal with any sudden disruptions, they're actually really good models. So when we're talking about chemostats or CSTRs that you're familiar with, those tend to be steady state, always in exponential growth phase, and these models actually deal with it pretty well. Perhaps not so well for a batch phase that goes through all of the different components of growth. Only really for the...
Batch phase.
Well, for batch phase, and we'll talk about ways that you can model the different component, like the different parts of the growth curve. But typically, the simpler models don't cover all of the extremes as well. So you can still get to parts of it. Again, lag phase tends not to be modeled well in general, but past the lag phase, we've got some pretty decent models. I wouldn't say 100% perfect, but in many cases, probably good enough.
So what would batch fall under in terms of structure and unstructured?
So it depends which part of batch you really care about. If you're not getting to the death phase too much, you probably could still get away with unstructured, unsegmented, but if you really care about what's happening precisely throughout it, probably segmented is more effective than unsegmented, so that's where you look at the individual cells. You may, depending on what the changes are throughout the batch, you may need to understand more about the biochemistry and what's happening with organelles and cell adaptation. So like remember when we talked about how given time cells could actually adapt to a wider range of pHs and still grow in a wider range of pHs? These models don't cover that particularly well. But if you start using structured models that understand the biochemistry and the different genes can get expressed having given different signals, then that can be more effective. Okay. Having said that, we're not going to do any of that. So we're not going to touch segmented models, we're not going to touch structured models, we're definitely not going to touch structured and segmented models. Those are way more complex than this course allows, but I do want you to be aware that they exist and that people are doing some really interesting research on them. Yeah.
Are we going to talk anything about controlling bioreactors, like control systems, or is that more for repeat?
No, we're really not going to do any process control per se. There is, when you take process control, sort of near the end of the course, they might start talking about model-based control and predictive control. And you could see where some of these model systems might be used in a process control scenario. But honestly, the controllers that are on the bioreactors that you're using, that you use in 4L and that we're gonna use in 4LL. Those are very simple controllers. They have a probe, they take a measure. It's just like your fridge or your thermostat. They have a probe, they take a measurement. It's off the measurement, it's too acidic, they add an AOH, they take another measurement, they stop adding it. So in that case, it's just they're expecting basically a near linear response, which is not entirely accurate.
Are they just PID controllers on those, or?
They're just PID controllers. So not perfect, but you know, pretty good. It's where you want to be able to control changes and deal with disruptions and stimulate changes to the system and bring it back under control. But you need to have more fancy control, like model-based control. Otherwise, it goes off spec and you just pump more water at it, or stop pumping and hope for the best. So I would say currently, most of the control systems on reactors are not terribly sophisticated. They keep the temperature about right, they keep the pH about right, but beyond that, maybe they keep the oxygen, but maybe not, probably not. Not in my experience, anyway. Yeah.
So when you're buying these software packages, there would be like,
Great.
or will have one that's not structured segmented, like, or do you like have to choose and like set it up differently? You said the equation, but you're like.
I don't have, honestly, I don't have experience with that. So I have not seen off-the-shelf structured segmented models. That doesn't mean they don't exist.
I just mean like in general, like with these 4 options we now have, are these like software packages?
No, I would say software packages still remain largely in this realm. It's when you start getting into research that you start looking at those other realms. So those tend to be more at the research level. But I think they're all, in many ways, like as computing power gets better and people get more sophisticated about understanding the actual biology of the cells, you're going to get closer. People have actually been talking about developing in silico models so that you don't have to do, for example, animal testing or even cell testing. So they have tried, that's one place that actually they really do try, especially to use structured models to try and say, if we add this drug, now we can predict just by typing it into the structure into a computer what will happen to the biochemistry of that cell. I think that's really in its infancy.
Don't they have to like do that by just trial and error and program that in the computer? Or are they trying to get that?
They're trying to, some people are trying to make models that are predictive, so that basically, I mean, ultimately their goal is to have a very sophisticated model that understands the biochemistry and the cell-to-cell communication of larger organisms, so that we don't have to do animal testing. That's way off. It is. It's way in the future. But people are trying. So there's research in the area, and it's lucrative because people spend a lot of money on animal testing and people testing, and there are ethical issues with it. You know, cute little hamsters, they don't want to die. So that people have a strong motivation to try and get as far as they can with it, but it's, I would say it's still in its infancy. Okay, so we're back. We're gonna spend all the rest of our time in that quadrant. Just, I do want you to be aware of some of the limitations of that approach, but it is a very powerful approach to help you understand what's going on in bioreactors in general. Okay. So, we've got, this is going to look really familiar, glucose concentration. So, basically substrate, right? And we've got growth rate. increase the glucose concentration, what happens? Does our growth rate go, does it start here, does it start here? No glucose, do you have any growth rate? No. So you add a bit of glucose, what happens to your growth rate? Goes up, and then keeps going up. Does it go up rapidly or gradually? Yeah, really rapidly. Then what happens? You add more and more and more and more glucose. Well, even before it becomes toxic. Yeah, the cells are actually just not capable of using the substrate at the concentrations that it is. Eventually, in fact, as we were discussing, it's like you were here, Carl, with him being here, it does eventually become toxic. Okay, so you can actually just look at that and say, what sort of mathematical model can we put to it, and do some empirical modeling to figure out the numbers. You can also look at it and say, gosh, that looks familiar. It looks an awful lot like enzyme kinetics, right? And we already did some modeling of enzyme kinetics. So it's maybe not surprising, actually, that cell growth would follow what happens with enzyme kinetics, because a lot of the growth depends on enzymes, right? So shockingly, perhaps not shockingly, one of the most basic models for cell growth, so there's your specific cell growth, says that you've got a maximum amount of cell growth times your substrate concentration over Ks plus S. Looks familiar, right? So I don't know if you remember when I was talking about the KLS kinetics, every once in a while I'd have a slip of the tongue and call it monokinetics. This is monokinetics. So he's the guy who said, gosh, that's a really good model that covers most cell growth. So what's the response to increasing substrate concentration? Eventually it levels off. That equation actually covers that behavior pretty well. And as you can see, it's covering the whole population. There's nothing fancy about what's happening inside the cells. It's just saying you put more substrate in, that obviously we're assuming that this is the limiting substrate, glucose concentration. Okay. Now, what might happen is you might see some really weird stuff happening here, because up here, glucose is no longer the limiting substrate concentration. Maybe you start seeing something else become the limiting substrate concentration. So you might end up seeing some behavior you're not expecting if you've got micronutrients that end up limiting the growth. It could happen experimentally. But what we're doing when we do these studies, describe these behaviors, is assuming that everything else is there in excess, and only the one substrate that we're interested in, usually our carbohydrate source, is the thing that's actually limiting the growth. Any questions? Make sense? Everyone's good with that? Okay, so I'm going to go fairly rapidly through the rest, because you've seen the development of the equations. You know how the behaviors happen. And the same basic things happen with cells as happen with enzymes. So what's one way, actually Carl, you already said it, what was one way that you could see cell growth being limited? Good notes. Impressive. So you can have substrate limited growth kinetics. So that's the no. Okay. So if you have relatively slow growth and you have a relatively low population density where the cells aren't particularly interfering with each other, monokinetics is pretty good. So slow growth, low population, minnow is pretty good. But if the cells are there densely and they're using up the substrate really rapidly, one thing that happens quite commonly as they're basically in a really hot burn is that they make toxic byproducts. So, they poop a lot and no one likes living in their own poop. So, if people are really spread out, they can, make a little hole and bury it and it doesn't bother anybody. But if people are packed in really tightly, it's no longer an option and it becomes really unpleasant, right? So that's what's happening to your cells is they're all, in some cases, if they're all packed in tightly, growing really rapidly, they make a lot of these toxic byproducts. So it's not, in here, it's not necessarily that the substrate is directly limiting it, it's that the result of lots of cells and the substrate are limiting it. Okay, so in that case, we've still got the mu-m and the substrate on top. What would you expect to be different on the bottom? You could have, and actually in some substrate inhibited, we're going to come to a different substrate inhibited model where you do. In this case, the way that they describe that there's an influence of substrate is they actually say, okay, what if you start with a really high concentration of substrate? If you start with a really high concentration of substrate, then you're likely to have a more inhibitory situation because right off the bat, everything grows like stink. Whereas if you start with a lower concentration of substrate, then you're going to have slower growth and fewer, slower byproducts pushing up. So what they did there is they said this Ks term is actually now a Ks naught, and it gets multiplied by the initial substrate concentration. The rest looks the same. So this model, the substrate limited model, basically the poop in your own house model, says it's problematic. Basically your growth slows if you start your cells off with a lot of substrate. Whereas you have more closer to Monod kinetics, more classic kinetics if you have a relatively low initial substrate concentration. Sort of conceptually makes sense to everybody? Awesome. Okay, there are lots of people spent lots of time coming up with their own equations that they thought model things just a little bit better, especially in the area that they're really concerned in. So one that actually, mathematically, is to do the least squares approach and see where you get the most error, that actually does really well, is really simple. It says, okay, you get past a certain substrate concentration. It's basically no longer dependent on the substrate concentration. After a limiting point, it doesn't matter, right? You can add more substrate, you're still going to have your max growth rate. That's just what your growth rate is going to be. Before that point, you basically have a more or less linear response as well. You double the amount of substrate, you double the amount of growth rate. Okay? So what they did there is they said, if S is greater than or equal to 2 Ks. So remember, Ks is where you're at half growth rate. That's Ks usually. If you double that amount of substrate, then you start using that line. Okay, so that line is just your growth rate equals your maximum growth rate. So it's basically saying the limiting point beyond which you suddenly have more than enough substrate and it's not limiting is 2 Ks. It's, it's not perfect, but it's pretty good. veer off a little bit right into 2KS, but for most of that regime, it actually describes it pretty well.
This is still substrate limited? This,
Oh, no. So this is, we're talking about a completely different model.
so what is this?
So this is just a completely empirical model that is another description of what people saw when they looked at how cells grew in response to more and more substrate. Yes, it does, actually. It is the Blackman equation. Good question. Gotta give credit where credit's due, right? Okay, so the Blackman equation says it's really easy. If you have enough substrate, you just get to your max growth rate. And then if S is less than 2KS, then we still have a pretty simple thing. Our growth rate is our max growth rate times S divided by 2KS. Okay. So basically, it's directly proportional. Our growth rate is directly proportional to the substrate concentration before this 2KS point. And it actually describes the data really well. Like I said, if you go through sort of what's happening all along here, you'll probably find less error by using the Blackman equation than you will the Monod equation or even the substrate limit equation.
Is this just a general model, or is it for a specific case?
So this is just describing what happens to cells when you add more and more substrate to them. So it actually could describe what happens when you add more and more oxygen. You know, I told you after you get to a certain amount of oxygen, then it's no longer dependent on oxygen. Same thing is true with glucose. You get enough. After a while, it doesn't care anymore. They just sit there and they're at their maximum growth rate. So all cells get to a metabolic point where they're physically not capable of growing any faster, no matter how much extra of anything you give them. Just
When did you use this one as opposed to another?
Okay, so that's a really good question. So I told you that one's better mathematically. Why might there be problems with this?
Measured leveling off phase there, we had the
So it's discontinuous, right? Here, right when you're around there, you actually have it transfer very abruptly from one regime to another regime, and it also doesn't describe the behavior very well at that point. Okay, and if you're trying to use the model as a control system, or if you're trying to do some math to integrate, which we're going to do, it's really hard to integrate a discontinuous system. It's possible, you just do it in two parts, right? But it's possible by hand. It's much more difficult to do that by computer. And when you try and use a discontinuous description by computer, there tend to be real disruptions to how well a control system can work. So although it might describe the data better, it can be harder to use. It's just not as nice to use because of that one point where it switches. Okay, so there's the Blackman equation. And then a bunch of other people piled on board and they said, I can do better. And I think in particular what happened is they were trying to develop general descriptions that apply to all cells growing on all media. But everyone was interested in their own particular system, and they were finding that, gee, the Monod equation didn't really really describe what was going on very well. And they would come up with this new model that described their system and simpler systems. So everyone just kept throwing in, you know, the sort of classic rule of mathematical modeling is the more variables you throw in that you can fit, the closer you can get to modeling it perfectly. So a little bit, I think that's what happened in this field. So there's the Tessier equation. So here we say mu g equals mu m 1 minus e to the minus ks. Okay, there's the Moser. I think also they all wanted their names on an equation. I too can have my name on an equation. I just have to come up with a system that's not well described by one of these equations.
Is that K times S or KS?
K times S. So this is a big S, not a subscript S. Okay, S to the n over KS plus S to the n, which if you rearrange is mu n. Okay. If you take a look at the Moser equation, if you just set n equal to 1, then you're back at the Monod equation. So it's a more general form. They've thrown another variable in so that they get a closer fit. Means it's slightly harder to use experimentally because now you have to you have to do more measurements to figure out what that n is. But it describes more systems and more conditions a little bit more closely, as you might expect when you throw another variable in. Okay, and then the most general, oops,
Does that mean that one can be, the node can be rearranged that one as well?
it
Well, without the n.
should be able to, I would think
So
so.
that one minus n. correct?
Yeah. It would still be in the -1, so ks over s. Right? I think that. I'd have to do a little bit of math. Feel free to do the math. I'd have to just double check, but I don't see why it wouldn't. For my own peace of mind, I'd want to work it out. But conceptually, it seems like it should, doesn't it? Okay, another. Got E, S, K, S, X plus S. So now we don't actually have more variables thrown in, but we have a new, well, we sort of do. We have a new thing that Control is suggesting influenced the rate of cell growth. And that's the amount of the concentration of the cells that you had. So as you get more and more, basically what this is saying is as you get more, your cells get more and more and more concentrated, you're going to have slower and slower and slower cell growth, which kind of makes sense, right? You know, as your cells get really dense, it's a different way of framing the substrate limited. You know, if they're really close together and they're having a lot of poop, then they're not going to be very happy. So rather than saying it's dependent on the initial substrate concentration, they're saying more directly, you know what, let's just put in what the cell concentration is, and that'll get you a better model of what happens, especially at high cell growth rates and high cell densities.
KSX, it was KS.
Because Contois came up with it,
So it is
so it's,
different though?
yeah, it is, I mean, it'll give you a different number. So you have to do modeling of your system to figure out what your KS is. And if you model your system with an X in it, then you're gonna end up with a different K than if you don't model your system with an X in it. So that's why the X is there, because it's saying that you're doing the modeling with cell concentration there. Make sense? Okay, yeah, eventually, as you use up the substrate and use up the substrate, so as S approaches 0, your growth rate becomes proportional to 1/x. So right at the sort of end of this, potentially describes the end of a batch reaction a little bit better. As you use up substrate and use up substrate, the more cells there are, the slower your growth rate is. Which, you know, is okay. And then so other people looked at all these equations and went, gosh, a lot of them look kind of similar. Maybe what we can do is put them all together and say that it's just one general equation, and now we look at all the parameters that we might want to fit. So here,
What was in general is?
this is generalized specific growth rate equation.
What's that? You just drew it.
That is like a new.
Oh, okay.
What epsilon? It might be an epsilon.
Possibly.
I think you would be safe going with an epsilon, because it doesn't look like a baby either.
Oh, so yeah, probably.
I think it's an epsilon. I don't know why. I have to say my drawing of Greek letters is not the best. I have to relate it.
Is that another epsilon?
These are all the same. That, and that are all the same.
Wait, I'm gonna go, we call it A.
Call it anything you want. Or you could just put mu-G-O-U-M every time I say it. Okay, so there, K, A, and B are constants. So I'm not gonna write it out, but on table 6.2 of your textbook, it actually says what A, B, and K are in each of the equations that have been described. So in Monod, I'll just say Monod as an example. So for Monod, A is 0. Okay, so that gets rid of that part. B is 2. And K equals 1/KS, of course, why wouldn't it? So you can go through and say what, in each of those equations, what the A, B, and K are in equivalence for the Monod equation, and your textbook has that. Okay, so I just did a whirlwind tour of the basic descriptors of cell growth. They all should look kind of familiar. We've looked at this sort of thing before. Next class, we're also going to start talking about models with growth inhibitors, substrate inhibition, product inhibition by toxic compounds, and then we'll start talking about what happens and how we use these models once we actually put them into reactors. Okay, any questions?